Well, hello everyone. This is Randy Riddle, and today I'll be speaking about post-wildfire soil degradation, erosion, and hazard for sedimentation and debris flow. Here on the cover slide, there's a photo of the Thomas Fire, which occurred in coastal California in December of 2017 into early 2018. I took this photo actually in the town that I live in Ojai, California, and you can see the scale of these fires in the wildlands. So the purpose of this discussion is that over the last few years, there have been several megafires, particularly in the western United States. Uh, the last year alone in California, the acreage record for wildland fires has been exceeded with the Thomas Fire, and then more recently with the Mendocino complex in the northern part of the state. Most recently, we've had more destructive fires in populated areas near Malibu at the Woolsey Fire, and in Northern California in the Sierra Nevadas in the Camp Fire, where an entire town, Paradise, California, was completely burnt to the ground. Due to these fires, there is significant soil degradation and ecological impacts, and we'll talk about some of these impacts today. So there are physical, chemical, and biological degradation processes that occur. And because of this, there's a high potential for soil erosion and overland flow or runoff. This can be in the form of sedimentation, debris flows, and of course there's the vegetative fire succession models that occur. In addition to this, there's also significant risk to human life. Currently, there's still a recovery effort in Paradise, California, where there's an unknown death toll, and that entire town was completely leveled. As we get more rain, there's going to be more hazards due to runoff and erosion. So here we'll talk about some factors influencing the increase in wildfire frequency and the sheer size of these wildfires. To the right here, we have a photo that I took out in front of my driveway last year during the Thomas Fire, burning on a mountainside that butts up against the edge of town, and several orchards that extended up into the foothills, many of which were burned. So part of the problem has been climate change. We've had prolonged drought conditions, so very dry vegetation in the hills, which creates a very large fuel load. There's also been shifting land use as development has expanded throughout the area, and agricultural encroachment into the wildlands, particularly in this area where orchards, mostly avocados and lemons, have encroached into the foothills and up into any usable land in accessible mountainous areas. And there's quite a few geomorphic factors at play, such as the slope, the density and type of vegetation, and of course the sheer size and the area of the wildlands that are impacted. Some factors of wildfire and post-fire soil degradation include, first off, the burn intensity, which is just a measure of the energy that the fire has. And that'll impact the burn severity, which is the impacts on the ecosystem and the environment. That includes the soil impacts. As far as soil goes, most of the changes occur at or near the soil surface, and with burning off the vegetation, there's a change in the surface cover. Those are very important controls for infiltration, runoff, and impacts and potential for erosion. So now we'll talk about some factors of post-wildfire soil erosion. One of the main factors is the loss of surface cover. And now we have less surface area, so water will run off quicker. There's less surface roughness, which would have formerly slowed down the speed of water of overland flow. And because of this, we have reduced surface aggregate stability, and which will lead into soil sealing, and which reduces porosity, increases bulk density, and of course an ignition or loss of soil organic matter. So everything kind of goes hand in hand uh, during a major fire event. A result of this is soil sealing, which is a major soil degradation factor. The detachment of soil particles tends to clog the soil pores at the surface. And there's a variety of reasons why this occurs, and we'll talk about this in more detail as the presentation progresses. There's also a temporary ash layer immediately after the fire, and these ash layers can, at first, they can reduce the rainfall impact, and they can absorb water, but it is eroded quickly, and then we have a bare surface remaining afterwards. We have reduced aggregate stability. We've already mentioned a decline in the soil organic matter content due to ignition and the bulk density. So some other factors of wildfire soil degradation is the degree of soil sealing. Now this has been described as probably the most important factor for soil degradation and erosion processes following a major wildfire event. Since the roots are burned off and the soil is less stable, there's more of a chance for detachment of particles that will clog the soil pores, which will kind of exacerbate itself and increase the potential for runoff. This degrades the soil structure and the soil stability. These processes elevate the bulk density, and it will reduce the infiltration rates. Other factors of post-wildfire degradation, and there are heat-induced changes to the soil properties. Most notably, people are familiar with the release of hydrophobic compounds, which promotes water repellency, which we'll speak in a little bit more detail very shortly. The hydrophobic compounds can be species dependent, for which whatever plant community was burned, and it also is dependent on the maximum temperature that the fire burned at. Other heat-related property changes are the ignition of organic matter. Obviously, the hotter the fire, the higher degree and amount of the organic matter that is burned off. And so there's also the amount of ash that accumulates at the surface can be impacted by how hot the fire burns and also the density of the vegetation in the area. So next we'll speak directly about water repellency. At first, much of the research in the area of post-fire soil erosion was based on the idea that water repellency was the main factor creating and causing the elevated amounts of soil erosion. And it was measured using critical surface tension, or CST for short. And as the plants burn, it releases these hydrophobic compounds, which will reduce the infiltration rate. It will increase the runoff impacts. And it's generally concentrated at or near the surface. I have some figures that are coming up here, and we can see that the water repellency is mostly isolated in the upper 3 centimeters or so, and it decreases with depth to almost no impact after about 6 centimeters. And water repellency has been measured as declining over time. It's most significant in the first year after the burn. Continuing this discussion, water repellency is also difficult to quantify at the watershed scale because it is highly heterogeneous across space. Now, most of the measurements in former research was done at the point scale, and it's very diverse with various degrees of water repellency across the landscape. So go from a very small scale site or plot size reading, and then we try to scale it up to the watershed size, and we lose our accuracy. So it's a difficult property to quantify. And some of the recent research has also suggested that the water repellency isn't as big of a factor as previously thought. There were some studies done on raked hillsides versus areas with repellent soils, and they had similar amounts of runoff that were measured in those areas. So this property was somewhat overstated historically, and recent research has proven that. Here we have a diagram of their critical surface tensions of a post-wildfire area. This is from Larson's research. And in the diagram here, the surface is the circles, and a lower CST value represents more hydrophobicity or water repellency. So the square is at 3 centimeters at all times is greater than the surface. So you can see that at the surface there's a greater degree of repellency over the period of the study. The gray blocks are the sediment yields from this area. We can see that they degrade or they decrease over time also. Next, we'll discuss the removal or burning off of surface cover. Bare surfaces will increase the overland water flow, and this is mostly due to reduced surface roughness, which has less surface area, and this is going to increase our runoff potential. With a bare surface, this will lead to soil sealing, and which will increase the impact and the ability for rainfall impact intensity. It will increase that, and it'll also increase the potential for splash erosion, which will lead to clogged soil pores and increased bulk density. This, in addition with the reduced organic matter content, will reduce the surface aggregate stability and degrade the soil porosity. The surface ash, it occurs generally at the surface, and it's just residue after the vegetation has been burned. It generally washes off after a few precipitation events, depending on the rainfall intensity. And it provides temporary protection from the soil. Originally, the ash was thought to create artificial soil sealing, but more recent research has suggested that the ash particles are actually too large to clog the soil pores. So maybe that concept was overstated based on assumptions. This recent research suggests that the behavior of the ash actually protects the soil from sealing and erosion. It will actually reduce the rainfall impact, and it will absorb some of the water and reduce the runoff. It's kind of a temporary situation because it will be removed with the runoff, and we've already mentioned that the particles are too large to clog the pores. So now we're going to discuss some factors that impact the erosion and sedimentation in the post-wildfire environment. Already we've mentioned the degree of soil sealing is the most important factor, and this was suggested by Larson's research in 2009. Before, a lot of the research was focused on soil sealing. It's on water repellency and the ash covering. However, Larson's research suggests that sealing is the most important factor. The watershed size strongly influences the amount of erosion and sedimentation. The amount of surface cover that is remaining after the fire and the roughness can slow the water down or create a bare soil surface. Concentrated flow, this can be somewhat landscape dependent on how steep and isolated the stream channels are. And And of course, the rainfall intensity is another major factor in the degree and amount of sedimentation that will occur. The time since the fire event is also very important. This is partly due to the recovery of the environment and the decline in water repellency and other factors. So the environment will begin to heal over time. And here, the debris flows. The debris flows, they can be initiated from either from the surface runoff or from soil saturated caused debris slides, and that's similar to mass wasting, and it will pick up momentum as they slide down the mountain. And of course, this only occurs when the shear stress of the runoff and the erosion exceeds the shear strength of the soil when the mass wasting occurs. So next we have a diagram here of the peak runoff discharge based on the 30-minute rainfall intensity. And this is from Moody's research in 2013. And these values are consistent with the evacuation rainfall intensity orders in California here where I live when evacuations were ordered for potential for debris flows. As you can see, the values in red measure a significantly increased peak runoff discharge after rainfall intensity in the 8 to 10 millimeter per 30-minute range. So once we exceed that rainfall intensity, peak discharge significantly increases. And the hazard for debris flows. The picture on the right is from the debris flows in Montecito, California, last January in 2018. This followed the Thomas Fire and occurred up near Santa Barbara. As we mentioned, the debris flows, they can be either caused from overland flow or saturated soil that is broken free and it forms into a debris slide. And debris flows are sediment-laden flows of water that carry large amounts of gravel, boulders, vegetation, things of that nature. I actually drove through Montecito after the fires and give you an idea of how much energy is in these debris flows. There were boulders that were over 6 feet tall, and construction crews were drilling holes and blasting them apart because the equipment and machinery in the area was too small to move it manually. So very devastating when this occurs. There is some potential for mitigation for post-fire erosion. Much of it is mulch related. There's been some measurements out of Portugal that measure the cost effectiveness of post-fire erosion control. And straw mulch is a widely accepted method. Very useful because it increases surface roughness and it reduces the rainfall impact. And it can limit the degree of surface sealing and decrease the shear force of runoff. Hydromulching was highly effective. However, it's not very cost effective. It's extremely expensive. In some areas, it's not very accessible to be rolling out equipment and distributing hydromulches. Historically, reseeding hillsides was used, but more recent research suggests that reseeding maybe occurs at too slow of a rate and probably doesn't help out as much as we originally thought, or even speed up the process of revegetating the hillsides. So, in addition to this, there's engineering practices such as diverting flow using sandbags or K-rails and debris flow basins at the base of canyons entering populated areas. The Los Angeles area in particular and many of the cities in the West have large sediment debris flow basins. A couple of years ago when I was mapping in the Los Angeles area for the soil survey program, I was in the Hahamongna sediment retention basin. There was a large wildfire in 2009 the station fire, and it filled in approximately, I think it was something like 18 feet of sediment. And when we were out doing some soil descriptions, you could see the treetops. So give you an idea of how much sediment can come down these mountains during a high intensity rainfall events following a major wildfire. Lastly is application of PAM, or polyacrylamide. There's some debate whether how effective this is, but chemical application which can basically flocculate the soils and promote soil structure development at the surface can help reduce erosion. So a quick review. The rainfall intensity and the degree of soil sealing are the main factors of erosion and hazards for debris flows. Larson identified that soil sealing is the main soil factor contributing to post-wildfire erosion, and it's mostly due to loss of soil cover and the reduced amount of surface roughness. And some other important soil changes to keep in mind are the temporary water repellency, which will dissipate over time, surface ash covering, which will erode very quickly and be removed from the surface, and other soil property changes such as the increase in the bulk density from the sealing, decreased porosity, aggregate stability, and the ignition, which results in a loss of the organic matter depending on the temperature of the wildfire. Next slide has some citations from the literature that I used. And thank you for your attention. And please contact me with any questions that you have.